All right, so today we're going to look at implicit differentiation. So, what we've been used to is what you might call explicit differentiation. So, say, example, you have something that say y is equal to 3x squared. We have y as a literal equation in terms of x, and we just go ahead and we say, okay, I want to take the derivative. You guys remember the notation that we discussed early on in the course. Take the derivative of this side, and I take the derivative of the other side with respect to x. Okay. And so we say, okay, well, dy dx, or technically 1 dy dx. We never really saw, so we never really did this part here. We just went dy dx is equal to, and you can know the shortcut is just equal to 6x. Okay. So we were taking the derivative of each side with respect to x, which it really wasn't necessary for us to really write it like this as an intermediary step, but we were fine just going from here to here. So the purpose of implicit differentiation. So when we have certain equations that are not written nicely, where y is in terms of x, this is where it's important. And this is going to tie into, we're trying to answer the question, how does chain rule tie into implicit differentiation? Okay, so let's see. If we look at number 1, we have 2x cubed is equal to 2y squared plus 5. Okay. So up until this point, what we knew was to maybe write y in terms of x. And we could do this. The only thing is here is that we have a plus or minus square root going on here. So if we subtracted 5, we have 2y squared is equal to 2x cubed minus 5 divided by 2. So y squared is equal to 2x cubed minus 5 all over 2. And then, so therefore, y is equal to, now if y squared is this, then y is equal to plus or minus, because it's a even power here, so plus or minus the square root of 2x cubed minus 5 all over 2. And we can imagine that if we were to take the derivative of this, well, first off, if we wanted to do it at a certain point, it would matter. So it would simply matter at what point we take it. Looks like if I brought that over, it looks like it would have been, I believe, maybe a hyperbola, because I would have had 2y squared minus 2x. Or sorry. Scratch that. This is a cube. This is a square. So this is probably something pretty funky looking graphically. And definitely now written like this, I have two parts. I have to write y equals positive form of this and then the negative form of this. And we can imagine if we had now tried to take dy dx right now, it would probably be pretty nasty to deal with. So implicit differentiation says, let's do this instead. Let's differentiate implicitly. Okay. So take this problem and problem, and we'll move it over. We fit it all together. So this is the one way to do it that we've learned so far. Let's show the other way.
Are you going to the same answer?
Yes. Yeah, you should arrive at the same. It shouldn't matter which way you do it. That's a good question. It shouldn't matter which way you do it. So if we take, so let's say we take the derivative with respect to x of each side. Take the derivative with respect to x of the right-hand side. Okay. Whatever we do to one side, we do to the other. Okay. So what is the derivative of 2x cubed with respect to x? Well, chain rule says we have 3 to the front, we have 6x squared, and then times the derivative of the inside, which is just 1, right? Derivative of x
Why
is
do you have to
1.
do chain rule?
Because technically you always do.
Okay, when I say chain rule, that means the same thing to me as power rule.
Okay, I was like,
It has
that's
the
not
same
chain
meaning
rule.
to me.
Okay.
So we can call it power rule. So then we say, okay, this equals, now the derivative of this side with respect to x. So, okay, so the derivative of, and now we're going to distribute, so okay, the derivative of 2y squared plus the derivative with respect to x of 5. Okay, so here this is just 6x squared is equal to, so the derivative of this with respect to x is, okay, chain rule, 2 to the front, we would have 4y, drop it down power, and then don't forget the derivative of the inside, okay, which we would just say is dy dx. Okay, so we like say assume that y is probably in terms of x, so we say dy dx.
Why isn't this one?
Because we are differentiating with respect to x. That means that y could be in terms of x, so we need to make sure to obey chain rule to do that. For example, let me be even more clear. If we go to this previous step here, and I said the derivative of this would be like 6x squared. In fact, let me undo, make that a more appropriate size here.
Oh, times dx over dx, which is plus.
Yeah, so we have 6x squared, and then you write dx, which is a ratio of a 1-to-1 ratio. Okay, you could think of it like that now.
But why is that way on the other side? Like, I'm confused. When you say with respect.
Let's go ahead and
You
move the
write the
question.
derivative of y because you're doing the inside of the
No,
equation.
not the y, like the 6x squared and then y is it?
So complete this, and then the derivative of the constant respect to x, derivative of any constant respect to any variable is, of course, 0.
Then change x or we change x.
All right. So if you understand chain rule, this is the application here. So it's okay. The derivative of this. Okay. Well, first off, we're going to obey power rule or chain rule. I'm going to say chain rule. 2 to the front to get 4y, and then don't forget to take the derivative of that with respect to x. We may not know what it is. In fact, we're going to end up rewriting this whole thing so that we have dy dx equals blah, blah, blah. Kind of like we had if I wrote it. I didn't actually write it here, so that, because it'd be pretty gross to actually do the derivative of this guy. So here we go. So if we go, last step is to simply divide both sides by 4y. So dy dx would be equal to 6x squared over 4y. Okay. So written here, we don't have to worry about this plus or minus 2 separate equations. We don't have to worry about that. We can just go ahead and write it like this.
Exactly. Wow. So we would actually get that if we did that long way? Can you do it?
We're not.
I mean, I could do it, but if you were to do it, you should arrive
See
here.
it. You
Yeah.
don't have to do it.
No, we're not doing that.
Can we do it different?
I want to see it happen all the time.
But we have to
Because
do
how will it work if you have to do a plus or a minus?
Okay, so here we go.
He's doing it, not us. Yeah, that's what I'm saying.
Yeah, really.
Guys, there's too much of this chitter chatter going on right now. Yeah, chitter chatter is what it is. If you have a question, you can raise your hand and I will answer, but all these things being blurred out at once, not very helpful. You may think it is, but it's not. And some students may find it distracting. So let's do this. Okay, so let's just focus on just the positives. So if we say if I say, just focus on the positive one for now, so y is equal to positive root of 2x cubed minus 5 all over 2. Which I think it's more convenient for me to view it as with an exponent, so it's equal to 2x cubed minus 5 all over 2 to the 1/2 power. And if we took now, if we did dy dx equal to 1/2 of the front, leave the inside alone. Drop it down power times the derivative of the inside, which is going to be a quotient rule. Are you guys fine if I just break it up in my head? So I'm going to view this as 2x cubed over 2, which is just x cubed. The derivative of x cubed would be 3x squared, and the derivative of negative 5/2 is nothing. So then we would have I mean, you could write this as then flip it and make it what, positive 1/2. Yeah, that'd be fine. Yeah, so you have 1/2 times 2 over 2x cubed minus 5 to the positive 1/2 times 3x squared. And maybe just a matter of simplifying at this point. But you can tell this is not really an advantage to doing it this way. So if you notice, let's say you wanted to find the derivative at a certain point. So at a certain point, xy.
I think we just want to see if it actually comes out the same. Because I don't believe you. I'm curious. Can we just believe that?
What happened to us?
Look, it's not gonna happen, look at it. It's just not gonna happen.
It's gonna happen. It's gonna happen. You a lot more.
I did a new flip chart. Okay, that's fine. All right, so we're here, right? Yeah, so dy dx, yeah. So it's not going to look this similar because I have this guy in terms of x and y. Okay, but here's the main point. The main point to do this is because if I wanted to say find the rate of change or the slope of the tangent line at the point, say 2, 3. I can simply plug in 2 for x, 3 for y, and get it like that. Okay. A lot of unnecessary work to first off decide, okay, which part of the graph is this on? Is this on the plus square root part, or is it on the minus square root part? Okay, the point's on the plus, so okay, let me get rid of that. And then once I do that, then I can just plug in, let's say I think I chose the point randomly was 2, 3, plug in 2 for x, then find what the value of dy dx would be. Here it's much easier to just do implicit differentiation, and then say if you want to find it again at a certain point, plug in the point there, and you have it. Yes.
Why can't you do it the other way around? Like, why couldn't you solve for like y side? Like, why does it have to be?
Why does what does this
Like,
have?
No, like on the like simple side. Like you take 6x divided by 4y. Why don't you take 4y divided by 6x?
You mean 6x squared divided by 4y?
Yes.
I divided both sides by 4y because I want to know what dy dx. I want to know the rate of change of y with respect to x.
Okay.
Yeah, because remember, dy dx, we're talking about an xy axis, coordinate grid. That's going to give us the slope of any tangent line for any point.
But if it said dx dy, you would just
Dx dy is something we won't do. It's
I know,
not.
I'm just curious. Like, I don't actually know what to do. The order.
I mean, it's like saying this. It's like, oh, can you do run over rise? We don't define slope as run over rise. We define slope as rise over run. You could, but that's not how we define slope. Because for these problems, for math up to this point, we've always let if x be the independent variable and y be the dependent. We want to know how much the dependent variable changes with respect to the independent variable. It doesn't make, it's not very logical to say, I want to know how much the independent changes with respect to change in the dependent. It's not very logical. It's like saying, for example, time is one of the most common independent variables, right? It doesn't require anything. It just goes on. But say, and there's all kinds of problems. The height of a ball might depend on time. So we start talking about differentiation in the derivative. We're talking about, okay, the change in the height of the ball with respect to change in time. It just doesn't make sense to say it the other way around. So we're going to look at another one. Let's go ahead and look at another one. So let's say we take a look at number 3. Guys, let's not chit chat right now.
Can we do one where they're both very, like x and y in a single term? No, this 3. It doesn't have that.
Sorry, what did you?
Just move the y to the other side.
What did you want?
No, but I'm saying if x and like on number 5, where it's 3xy.
Oh, well, there's an xy term.
Like that, or is it just can we do one like that?
Can we do that next?
Yeah, I wanna go over.
3.
Because this is like the same.
I want to go over these one more. I guess I'm gonna have. If we wanted to take care of this guy, now obviously, if I try to do this explicitly, try to get a literal equation for y, it'll be pretty tough. I could bring the 5y over, I could factor out a y, but I still have a linear term that contains a y. So this is definitely something I want to just jump into with implicit differentiation. So if I go ahead and again, the idea is I'm going to take the derivative with respect to x, because x is the independent variable. I'm going to do that on both sides. I'm going to take the derivative with respect to x of the left-hand side is equal to taking the derivative with respect to x of the right-hand side. And this is just, of course, just the basic principle that you can do whatever you want to both sides of the equation. Okay, so in doing this, this is where chain rule comes into play. Is if I take the derivative with respect to whatever, I have to obey chain rule. I have to say, okay, and you may call it power rule, but I'm going to use chain rule moving on because chain rule encompasses, to me, that's power rule plus everything else. So 2 in the front, so 2 times 5 is 10. Y, this drops down, so we have 10y. Then we have to take the derivative of what I call the guts. Okay, that's chain rule. Working from the outside and keep going in, keep taking the derivative all the way to the inside. So here, times the derivative of y with respect to x. So dy dx. Equals, again, you basically apply the distributive property. So you have dx of 2x cubed plus the plus or minus plus the derivative of negative 5y. Okay, so let's go ahead and do this. So this would be the derivative of this would be, of course, chain rule or power rule for this chain rule. So 6x, drop this down, and then technically times the derivative of this. Well, the derivative of something with respect to that same variable, that's a 1-to-1 ratio as we saw in the previous slide. So you could write dx over dx if you want to start to get comfortable with it. But then once you start to do enough of these, it's like, okay, I get it. It's with respect to the same variable. I don't write anything. It's going to be 1, but we'll do that for now. And then the derivative of this guy is going to be, we say, negative 5, right? Technically, if you want, view it as a product. That makes it very clear. If you view this as technically -5 times times positive y, then you know you're doing it right. Okay, so it's like the derivative of the first is 0. Leave this guy alone, so that goes away to 0, plus leave this guy alone times the derivative of the second, which is dy dx.
So essentially you're like treating it like product rule as two separate things.
Yeah, you can play it safe. When you treat as product, you'll play it safe, and you'll get it right every time. Then again, it's one of those things, eventually, when you do enough of them, it's just like, okay, -5 dy dx. But I'm going to, present it in a way that's very broken down, very organic, and then go from there. So here we have 10y dy dx is equal to all of this. Again, this is dx and dx, that's a ratio of 1 to 1, just 1. So now it's just a simple algebra. Just I want to have dy dx on one side, and then everything else on the other. All right, I'm going to shrink this down a little bit. All right, and then so we bring over so I'm going to add 5, so 10y dy dx plus 5 dy dx is equal to 6x squared. And then now I can factor out dy dx. So dy dx times 10y plus 5 is equal to 6x squared. And then now, at the last step here, divide both sides by 10y plus 5. So dy dx would be equal to 6x squared over 10y plus 5. So let's say you wanted to find the slope of the tangent line at the point x equals 2. Hopefully they give you both coordinates. Typically they will. So let's say 2, 3. I could just go ahead and I could plug in 2 for x, plug in 3 for y. And I could actually find the slope of that tangent line at the point 2, 3. Yes.
Will you do number 5 now, because we haven't gone over one where there's an x and a y?
Yes, that's a good one to look at. We'll look at that next.